Burhan, and also thanks in addition to inviting me for this session, and this is my first attendance to a TASSA event, and it's been since yesterday. I was incredibly impressed and immensely pleased with both the diversity as well as the contents and the substance of all the talks. And even though it has been a diverse crowd audience, the speakers have done a wonderful job actually in relaying their messages to the audience, and I was also very impressed by the young scholars and their presentations. So I would like to congratulate you and TASSA and all the leaders of TASSA for this major accomplishment. So what I would like to do, this is the title of my talk, Stochastic Themes and Games with Asymmetric Information. You have at least heard the words stochastic and asymmetric in Burhan's presentation. I would as well have called the talk Distributed Decision Making and with Asymmetric Information. And this is going to be a fairly high-level talk given the diversity of the audience. And what I would like to share with you is the research landscape I live in as it pertains to the topic of the session, which is optimization. I'll try to relate what I'll be talking about to optimization. So the first thing, one of the landscapes, research landscapes I live in, is the decision and control, and let me tell you just a little bit about control. This is the classical paradigm of control, which goes back to the 1950s. All the major, at least, approaches and results were initiated then. You have a plant, and this could be an engineering plant, but even though this session is on engineering optimization, it could be an economic system, it could be a biological system, and what you do is you collect information on the plant, and you don't know everything about it, and then you want to feed back some signals into the plant or into that system so that it will behave in a way you want it to behave. And so for that you need definitely a mathematical model of the plant, and this is never an accurate model. And you will need a mathematical model for the information that you collect on the plant, and that is the sensor model. And there is this, what I have here as the plant uncertainty. There are unwanted, undesirable inputs into the plant, which you may not be able to model, and some of it may be due to adversarial impact on the plant. So the main issue is how one designs this controller or this feedback mechanism. In fact, we did hear about the feedback yesterday from Kenan Shahin, mentioned feedback in the context of democracy. So feedback is an essential component of any successful design, because without feedback it is not possible to have a stable world. And likewise, you cannot have a stable system without feedback. And stability is very important. And after stability comes performance. You have to have a stable system, but then the question is how can we improve the performance of the overall system? So here is where optimization comes in. And what I want to point your attention to is that this is a dynamic optimization problem. This designing the feedback is a dynamic optimization. Why dynamic? Because you are receiving information from the environment, from the system that you want to control, and then you want to optimize the performance, and so one has to have some performance measure to be able to optimize it. So this is the control part, and there is now comes in games. If you want in this scenario, the paradigm that I just explained, you have a single input into the system. It could be, but it could be multiple inputs, but controlled by a single entity. Now, if you want to extend it to scenarios where there are multiple agents and who are interacting with each other, who are interacting with the system, then we are in the paradigm of games. And we did here, at least the games were mentioned earlier in this conference, in this meeting, both yesterday and in fact also today in the context of kidney transplants. So they go, decision and control really feeds into games. And most of the developments in games, at least the scientific approach, was again in the late 1940s and early 1950s. And John von Neumann is known as the father of game theory, and I'll say something about that shortly. So what game theory deals with is quantification and characterization of interactions between different entities. We call them players, we call them agents sometimes, and or even decision makers. And these are strategic interactions. They have to anticipate what others will be doing and act accordingly. And this happens over in a dynamic environment and an uncertain environment in general. Here I list a number of different types of games and the issues that come with. There are zero-sum games where what one gains, the other one loses. You have non-zero-sum games where everybody could win, and but it's a strategic. They don't win by the same amount, and you have games where you have total lack of cooperation. That's non-cooperative games, and you have the cooperative games. And complete games where there is complete sharing of information, one where players are not aware of even what game they are playing. So this is the incomplete information games. Deterministic versus stochastic, and static versus dynamic games. And the issues of bargaining, this happens in cooperative games mostly, the bidding. Auctions, we have heard about auction theory yesterday in one of the talks. So I mentioned John von Neumann as the father of game theory. In 1944, he wrote a very influential book with Oscar Morgenstern, and this is a quote from von Neumann. He actually viewed life and nature as playing a zero-sum game where the physics provides the rules. Okay, and this feeds in naturally into economics. We had a session here in economics, and game theory actually started within the field of economics, motivated by problems arising in economics. And this is again a quote from von Neumann. Economics is the study of how organisms and organizations develop strategies that increase their chance for reward. And this definitely involves optimization. Again, this is related to the theme of this session. And here this is economics, but evolutionary systems, biology, again fits into the same framework where the criterion there is survival. That's how species evolve. And you, again, the game theory is a very natural, provides a very natural setting to study problems of this type. And there's a whole branch of game theory called evolutionary games, where you do, motivated by how species evolve over time, you extend these to other scenarios. So, but the important thing is, again, there is optimization. Okay, so now here I have a fourth actually element coming in, which is communication. And without communication, if you have a game scenario where you have multiple agents, well, they have to communicate with each other in order to be able to accomplish something. So the communications is, again, a very important element of this bigger picture. And when we talk about communications, and again, I want to relate this to what was mentioned at least briefly yesterday. The name of Claude Shannon was brought up by one of the young scholars, and then in another talk. And this, again, is in the late 1940s. Shannon introduced this notion of transmitting information over a channel. So in its most simplistic terms, you have a source which sends out bits or information in whichever way you want to model it as a random process. And then you have a channel that it is transmitted over, and you have to massage this output of the source or shape it. This is called encoding or coding. And then you send it in a way so that there will be as little distortion as possible. And then at this end, this is the receiver end, this is the destination, where the D stands for decoder. You have to decode the message. And so transmission of information over a noisy and possibly unreliable channel. More recently, work has been devoted to problems where the channel is actually the disturbing noise is not a statistical noise, but is something that's picked by an adversary. And so you have to transmit it with high fidelity and using the appropriate encoding and decoding schemes. And this is, again, an optimization problem, because you can optimally, you have to optimally design E and D, these boxes. And of course, there are different, this is in its simplest form, but Shannon's approach was not that. His approach was to find the best possible performance you can get out of systems of this type, and then the question is, how can you achieve that performance, whether you can achieve it using simple encoding rules. And this, I wasn't planning on talking about it, but this Burhan's presentation of this kidney transplant, where the patient has the option of making a decision whether to accept it or not, depending on what will happen in the future, is something that is relevant in this context also. And you can extend this to general sensor networks. And in sensor networks, the sensors, when they want to collect information and want to send it to a destination, they have to decide, because of battery constraints, the usage of battery power out in the field, they have to decide whether the information that they have received will be useful at the destination or not, whether they should transmit it or wait for the next one to arrive. So this is again an optimization problem, a trade-off, and so on. So now wrapping around all of these is the multi-agent networks, which is a very hot topic now, and multi-agent networks are describe scenarios where you have multiple nodes, but each node could be, for example, an engineering system, could be a control system. Each node could have a dynamics within itself. It could be static, or it could be mobile, and they have interactions. These different nodes have interactions with each other, and I believe Asu is going to talk about networks in greater detail. But what I want to say at this point is that when these different nodes are connected, they are connected in three different ways, and you have an underlying topology here, and these are whether you have they connect through communication. This is would be a communication graph. Whether you have a description of whether two nodes are actually collaborating each other in decision making or not, or whether it's a physical connection, which means the actions taken by one node affect the other one. So you have layered graphs which arise in this case, but each one of these is actually a separate, could involve a separate optimization problem, but then you have to optimize the overall system, both the topology as well as the interactions between these different nations. So agents. And there could be, I'm running out of time, and I want to say that some of these nodes could also be adversarial, so not everything could move along as perfectly as one would have expected because of the intervention by the adversaries. And this leads to a game situation. You have a zero-sum game or a non-zero-sum game, depending on how things evolve. And some examples, very sort of quick snapshots of different networks. The power grid constitutes a network. The internet constitutes a network. And without feedback, internet is not usable, and in fact, in the it started as an open loop system. In the mid 1980s, there was an internet collapse, and then it's when the feedback was introduced into the internet, so that you can all comfortably exchange messages with each other. There's transportation networks, airline networks, and the smart grid. Energy networks, I think John is going to talk about the energy systems in greater detail. Social networks, so it's not only engineering where this line of research applies to. Epidemic networks, quite a bit of recent research on this, and how one can actually stop the spread of epidemics, and how can you cure things under, again, resource constraints, and economics and financial networks. So I'm going to go very sort of give you this general framework for all these problems. You have multiple decision makers who pick policies, and then they lead to actions, and those actions evolve over time. And then the policies are constructed based on information that they receive, so that's where the communication part comes in, and this could be active as well as passive information, and the construction of these policies are guided by individual utility or cost functions, and there is a decision-making horizon, an optimization horizon there. In this scenario, if you have just a single decision maker, which was the control system that I had on the first slide, then this leads to a stochastic control problem. If you have a single objective problem but with multiple agents, then you have stochastic teams, so that was in the title of this talk. Otherwise, you have zero-sum or non-zero-sum games, and you have Nash equilibrium generally in the case of non-zero-sum games. And John Nash, again, is someone who made major contributions to game theory in the early 1950s. So the question is, how do you approach problems of this type? And I'm not going to go into details. I don't have as much time, but you ask yourself one question, and the answer to that question determines whether the problem that you will try to attack is a relatively easy one or a very difficult one. So the question you ask is the quality of active and relevant information that an agent receives in this multi-agent scenario, is it affected by actions of other players? If it is, then this is quite a difficult problem to solve. And I'll say shortly why. And if the answer is yes, no, then the underlying game or team is generally simple. And because it's simple, because you have the decompositions of these. So this leads to problems where the answer to that question is no. That is, the actions do not influence the information that's received by the players in the future, are known as neutral problems, and this is called neutrality in stochastic dynamic games. And here the measurements acquired by different players or agents are independent of the past decision policies. Okay, so if this is not the case, then the problem is a non-neutral one. In this case, the conditional probabilities, which are important, which is what players built their policies on, are shaped by past policies. So now, for neutral problems, there is the tool of dynamic programming. You can essentially sequentially, either temporally and also locally, as Burhan has told you, how you can locally compartmentalize optimization problems and then bring pieces together. So you can sequentially decompose the problem into static ones, and this is essentially the idea behind dynamic programming. And again, it was something that was developed in the early 1950s, and or in the game scenario, it's called a subgame perfect equilibria, Nash equilibria. So this leads to a piece-by-piece construction of dynamic policies. I want to add a footnote here to say that everything that I talked about, the starting point was in the 1940s, late 1940s, early 1950s, the John von Neumann's work, John Nash, and the control, development of control, and dynamic programming. And so there was something spectacular going on at the time, and Shannon's work, that people, even though they were not necessarily in contact with each other, and definitely there was no email that people could exchange information, still there was this huge, incredible dynamics drive in most of it curiosity-driven. Some of it was driven because of the Second World War, and but not only in engineering, but also in social sciences and economics and so on. So this is something to keep in mind. I'm not sure whether we will see since then major developments have taken place, but I'm not sure whether we will live the same era, that 10-year window, 10-year period that we had in the 1940s, late 1940s and early 1950s. We are building on that, and definitely the other optimization techniques like linear programming was also developed in that during that time because of resource allocation problems. So that's for the. So if a problem is not neutral, then you have a sequential decoupling and construction is not possible. So that's what the current researchers, my group is working on problems of this type. You have issues of signaling. In that case, the actions have multiple roles because when you take an action, a decision maker or an agent has to think of the consequences of that action, how that is going to affect the information of agents who will be acting in the future, and how that information is going to be utilized, whether it will be to the benefit of the agent who will be signaling that action. So there is all this tension between signaling and local optimization problems of this type. This is not I won't be able to go into details. So I had asymmetric information in the title. So this is one of the difficulties when you have asymmetric information, when the players do not share the same information, then you run into difficulties. At least there is no universal way of approaching these problems, and it's very much problem dependent. And also problems with non-classical information. These are the non-neutral ones where you have a decision unit's action affects the information of another agent. So many questions that we are addressing in this context: the existence of solutions, exists both team solutions as well as Nash equilibria, characterization of the solutions, and the robustness and resilience issues. How, when you come up with solutions to optimization, dynamic optimization problems, how robust is that solution if you change some of the modeling assumptions? And if there is any major collapse in the network, some links are broken, can the network recover itself? And the importance of network topology and so on. So these are the important things. And one fairly recent approach to problems of this type, the scalability is an issue, and when there is a fairly good number of agents in the system, then the problems become much more difficult to solve. But there is light at the end of the tunnel, and this is again a quote from John von Neumann from his book with Oscar Morgenstern on the theory of games and economic behavior. And he says he saw this in a different context, in the context of that he was looking at, that as the number of players increased, there was some difficulty in obtaining solutions. But he was saying if we have a very large number of players, so think of this network with thousands of agents, then things could simplify because the impact of each agent is infinitesimal, and this has led in both control and game theory, dynamic game theory, to what's called the mean field games. And indeed, this type of this observation does play an important role, and so therefore there is one way of approaching these problems is through this mean field game lens, which means that you do have further simplifications that run into that, just like the using the laws of statistics and probabilities, when you can come up with probability laws on the behaviors of the players. So I want to just leave you with one book which is related to some of the things that I have talked about here, but not everything, on stochastic network control systems. And Serdar Yüksel is a faculty member at Queen's and another Turkish scientist. And thank you.